Hey, welcome back for another lesson in our third unit in AP Calculus. You might be wondering where I'm broadcasting to you from. This is my garage converted into my youngest son's bedroom, and perhaps you can see a basketball goal, but I tell you, there's actually nowhere I can face where there's not a basketball goal in view. We had a tropical storm, so I couldn't go to my classroom and work in an office, so I kicked my son out. He was nice enough to offer, sort of. And I'm broadcasting to you from here. But let's continue learning calculus, whatever the situation may be, right? So if you know all your derivative rules and you're able to take a derivative properly, you're going to get like one question right on the AP Calculus test, because that's about all they'll ever give you. That's all you do is take a derivative. You have to be able to apply the derivative. Don't misunderstand me. Being able to take the derivative is absolutely essential, because you're going to have to do it on half the questions on the AP exam. But you have to do more than just take the derivative. You got to apply it. Apply the rules to different situations, apply the results, and interpret it. That's what it's going to be all about. So we're going to spend the whole lesson practicing applying these rules before we learn some new rules, okay? So here we go. Determine the points where the function f of x is equal to x cubed minus 12x has any horizontal tangent lines. So a horizontal tangent line is an extremely important situation, and we'll talk a lot about it in a future unit. But we need to know at least this much right now, that if I have a horizontal tangent line, that means the slope of that tangent line is 0. Can you see these places where I have a horizontal tangent line? The slope is 0. And you might also note that they're probably pretty important points in the graph, and they definitely are. So when they ask for horizontal tangent lines, we're talking about when does the derivative equal 0. So let's take the derivative. And I get 3x squared. When I bring down the exponent, subtract 1 minus 12. All right, now be careful here. Again, we're solving for when the derivative is equal to 0. We're not looking for the derivative at 0, okay? So set the derivative equal to 0 and solve. Okay, I'm going to divide everything by 3, and that's going to give me x squared minus 4. And I'll factor that as a difference of 2 squareds, x minus 2, x plus 2. And so you could see that values of x are x equals 2 and x equals negative 2. Sometimes that's all they want. So they'll say determine the x value. But this does not say that, so you want to be careful. This says determine the points, which means we need x comma y. So I need to go back and evaluate the original function at each one of these. So f of 2 is, let's see, 2 cubed minus 12 times 2. That's 8 minus the 24 is a negative 16. And f of negative 2 is negative 2 cubed minus 12 times a negative 2. So that's a negative 8 plus 24, which is a positive 16. So the points where you have a horizontal tangent line are 2, negative 16, and negative 2, comma 16. I can't leave it like that. Let's take a look at the graph. Let's pull up a copy of Desmos. Let's see if we can't graph that right quick. Alright. So we're looking at wrong page. Y equals x cubed minus 12x. Y equals x cubed minus 12x. And we said that we're going to have horizontal tangent lines at negative 2, 16 and positive 2, negative 16. Pretty neat, huh? Alright, moving on. Alright, your turn. Practice 2.1. Determine the points at which the function f of x equals x plus 2 sine x has horizontal tangent line. And we're going to constrict x to be just in one trip around the unit circles. That will vary from time to time, but there will always be a restriction. If I ever give you a problem where I forget to give a restriction, just assume it's one unit circle rotation, 0 to 2 pi. Go for it. Alright, let's see how you did. Alright, the derivative f prime of x, the derivative of x is 1. And then the derivative of the 2 comes along from the right. The derivative of sine of x is cosine of x. Alright, we need to figure out where this derivative is horizontal, so where does it equal 0? So I get a negative 1 is equal to 2 cosine of x. So that's a negative 1 over 2 is equal to the cosine of x. So when does that happen? Well, cosine is equal to negative values in quadrants 2 and 3. And so this is going to be at x equals 2 pi over 3 and 4 pi over 3. So now we got to determine the y value. So we got to do f of 2 pi over 3, which is 2 pi over 3 plus 2 times the sine of 2 pi over 3. Now, if this is a free response problem, y'all, I'm not going anywhere past this. But if it's a multiple choice, they will probably take it a little further. They'll get the sine of 2 pi over 3. That's in quadrant 2 where sine is positive. Square root of 3 over 2 times 2 is just the square root of 3. And, we could get a common denominator, make that 2 pi plus 3 root 3 over 3, but I'll just leave it like that. So that point is 2 pi over 3, comma, 2 pi over 3 plus root 3. All right, now the next one is going to be almost exactly the same thing. It'll be 4 pi over 3, comma, 4 pi over 3, but this time will be a minus root 3. And you can check that by plugging in if you need to. All right, for your next practice problem, for what value of x is the tangent line to this equation vertical? So you're going to think about what does it mean for a tangent line to be vertical? What are you looking for there? Pause the video, give it a try. Okay, they were nice enough to just ask for the value of x, so that's all I need. Let's rewrite this as 9x to the 1/3 power. Take the derivative. That's y prime is equal to, bring that down, 9 times a third is 3. X to the negative 2/3 when you subtract 1, and then the constant, derivative constant is 0. Alright, so in this case, I actually am going to rewrite this back with this on the bottom, because I want you to see it written like that, because it's asking where is the tangent line vertical. Well, a vertical tangent line occurs when the derivative is, the slope of the tangent line, I should say, is undefined, or in other words, the derivative is undefined. So for what values of x makes this undefined? Well, it'll be undefined when it's a 3 over 0. So the answer is at x equals 0. That is where the tangent line is vertical. Let's take a look at that one. 9 cubed root x minus 1. Right there you can see that it is definitely a vertical tangent line somewhere in there. That tangent line is going to be straight up and down. So that is also an important point. All right. Practice 2.3. Find the x so that the function, find the k so that the function f of x equals x squared plus kx is tangent to that. So think it out. See if you can figure it out. Okay, so hopefully you were able to figure this one out. The first thing I would realize is that if we're going to be tangent to this line, that means that the slope at some point on this curve has to be equal to the slope of this tangent line, which is 2. So the slope of the tangent is 2. Well, let's get the slope of the tangent line equation. The equation for the slope of the tangent line, I should say. That's 2x plus k. So at some place, this has to equal 2. Well, here's another thing that has to happen, is that this curve and this curve have to be touching. So at some place, x squared plus kx has to be equal to 2x minus 9. So I'm going to say 0 is equal to 2x plus k. I'm sorry, not 0. That's the wrong thing. What did we say the tangent line has to be equal to? 2 has to equal 2x plus k. But we also know that there has to be some place where x squared plus kx has to equal the y value at 2x minus 9. So 2 minus 2x is got to be the value of k that would allow this to happen. So I'm going to do that. I have x squared plus 2 minus 2x times x is equal to 2x minus 9. So I get x squared plus 2x minus 2x squared equals 2x minus 9. Alright, I can subtract 2x from each side. And I get a negative x squared equals a negative 9, so I get x squared is equal to 9. And taking the square root of each side, it's going to give me plus or minus 3. So I found that the x value where this occurs will be at plus or minus 3. So since k is equal to 2 minus 2x, we know that 2 minus 2 times 3 is equal to k. That's going to be 2 minus 6 is a negative 4. But there's another one, right? 2 minus 2 times a negative 3 is equal to k. So that's at 2 plus 6, which is 8. So let's take a look at that. So we're saying that k can be negative 4 or 8. So let's take a look at the graph and see if we can't figure something out. So we have x squared plus kx, and it lets me add a slider. So I'll add a slider. And then we've got, what's the other equation? Y equals 2x minus 9. Alright, so one of the values we found was k equals negative 4. So let's slide k down to negative 4. And we should see it start to get closer and closer to that line, and then eventually be tangent to it, right? Let me make that a little bit bigger. There we go. And so you can see they intersect right there at 3, negative 3, and they're clearly tangent. The other value we got, though, was 8. So how does that happen? Well, once you move this over to the plus side, you see it starts coming down on the left. And then if I get closer to 8, we're going to see them become tangent. Right there again. So two different places where this graph can be tangent. Kind of a tough practice problem. I don't think I'd feel too bad if you didn't get that one, but I wanted to give you a shot to try it first because it's kind of neat. Alright, next one. We're going to find a and b so that f is differentiable everywhere. Well, we know that to be differentiable, you need to be continuous and smooth, or have local linearity. Or in other words, you need to be continuous and have the derivative be the same coming from the left as from the right. So first of all, let's ensure that this is continuous, which means that the value on the left and right have to be the same. And that's going to happen at x equals 2. This is differentiable everywhere. This is differentiable everywhere. It's just the fact that they're at x equals 2, we have to switch between the two. So we're going to put a 2 in for x, and we're going to say you have to equal the same as when I put a 2 in for x here. So remember, these are continuous everywhere except for possibly where they're switching between the two branches of the piecewise defined function. So I get 4a plus 1 equals 2b minus 3. So that's 4a minus 2b equals a negative 4. Alright, I'll leave it like that. That's fine. Okay, so next we need to talk about the derivative. Well, f prime of x is going to be something like this. It's going to be 2ax, and then the 1 will go away, and then the derivative of bx is just b. So when x is equal to 2, I'll have 2a times 2 for the derivative on the left, and that needs to be equal to the derivative on the right, which is always just b. So 4a equals b. And so I'm going to use that, and I'll just replace 4a with the letter b. And I get a negative b equals negative 4, so b equals 4. I'm just slowing a system. I got a little lucky when I had a 4a there. Usually you have to put the 4a in here for b, but I can do that, right? And so since 4a is equal to b, then a is equal to b divided by 4, so a must equal 1. So our equation then would have to be x squared plus 1 and 4x minus 3. We can confirm that they're continuous. If you plug in a 2, you would see that f of 2 is 5. The limit from the left is 5, the limit from the right is 5, so the limit is 5, so they're the same limit as function value. The derivative would be 2x, which at 2 is 4, and the derivative here would be 4, which is always 4, so we have accomplished our goal. A stone is tossed into a lake from a height of 32 feet above the water with an initial upward velocity of 16 feet per second. The vertical position of the stone S is defined by this function, where V naught is the initial velocity and S naught is the initial position. Find the velocity of the stone upon impact with the water. So, pardon me to my science friends out there, I'm using not the official science units, I'm using feet here, but it's good to be able to go both ways since we still use both. So try and answer this question as best you can. Notice that V naught is that initial velocity I gave you, S naught is that initial height that I gave you. In AP Calculus, we're only going to be dealing with motion problems that are either straight up and down or left and right, never diagonal. So that makes things a lot easier. Give it a try. Okay, here we go. So my position function, S of t, is equal to negative 16t squared plus 32t. Oh, no, that's not the right velocity, is it? What was my initial velocity? 16. 16t and then plus 32. Now, sometimes these problems can be done without a calculator if they pick the numbers real carefully. Other times they need a calculator. So just when you're doing practice, if it looks like you need a calculator, use one. If not, don't. All right. We need to find the velocity of the stone upon impact with the water. So it's going to impact the water when S of t is equal to 0, right? Because we're 32 feet above the water, so this is saying that S of t equals 0. Well, we can solve for that. Fortunately, I can divide everything by a negative 16, so that becomes t squared minus t minus 2, and this one factors as t minus 2 and t plus 1. So I get t equals 2 and t equals negative 1. Well, clearly we're not interested in backwards in time. See, the problem is we're throwing the pebble from a height of 32 feet up here already, right? And so it's going to go up a little bit more and then come down. So this minus 1 time is saying, like, based on this parabola, what's backwards in time. So we don't want that one. We're saying t equals 2. Well, we want to find the velocity. Well, the velocity is the rate of change in position. So we can call it S prime or just V of t, but whatever it is the derivative of S. So V of t must be equal to negative 32 t plus 16. So it's, that's the acceleration due to gravity, right? And that's the initial velocity. So V at 2 is a negative 32 times 2 plus 16. Which is a negative 64 plus 16, which is a negative 48 feet per second. The velocity when the pebble reaches the ground, assuming no air resistance, is a negative 48 feet per second when it hits the water, I should say. Alright, so since we're talking about these kind of things, let's go ahead and nail down this relationship between the derivative and the original position function. The graph of a horizontal position of a particle moving along the x-axis is shown in the graph below. Sketch the velocity function for the particle. Remember a second ago when I said that we're only going to look at motion that's either straight up and down or left and right. So it's a little bit weird, this idea that my position function is a function of how far something is left and right, but I'm mapping how far right or left it is on the y-axis. So you can see that as we go around this curve here, this point here is 1, 2, 3, 4, 5. This is 6 up. So what it's saying is at this moment in time, the position of the particle is 6 units to the right of the origin. So just be aware of that. All right, so you graph what you think would be the velocity function. So pause the video and give it a try. All right, let's see how you did. So the velocity is the derivative of position. Well, this function here has, this part of the equation has a slope of up 1, 2, 3, it looks like over 2. So I'm going to go up 3 over 2 is 1/2. So from 0 to 1, 2, 3, 4. Now I don't really have a derivative at this value since it's just a starting point. So I'll make that an open circle. And I'm going to go all the way over to 1 to 4. 1, 2, 3, 4. And then I'm going to put another open circle because this is not differentiable right here. It's a sharp cusp. We have a derivative of 0 for 1, 2, 3 units, so I'll hop down here and make it a derivative of 0 for 1, 2, 3. Then we're going to hop back up to 1/2 for 2 units. So we'll go here for 2. And that's it. Okay, and that is all for this lesson. So I will see you for lesson 3.